Please be seated. Good evening, and a very special word of welcome to the Vice Chancellor and Principal, Professor Francis Peterson. It's a pleasure to have you with us. Welcome. Prof Peterson has been the Vice Chancellor for the university since the 1st of October. The Vice Principal, Research, Innovation and Postgraduate Education, Professor Sunil Maharaj. The Vice Principal, Academic, Professor Loretta Ferris. Members of the UP Executive, our speaker this evening, Professor Wynand Steyn, who is also the Dean of the Faculty of Engineering, Built Environment and Information Technology. I see all the deans here, so the deans and deputy deans, welcome. Good to have you here with us. Heads of departments, our academic and professional staff, and students. Special welcome to the family of Professor Steyn. Good to have you with us. Ladies and gentlemen, it is indeed wonderful to have many of you attending today's inaugural lecture to be presented by Professor Wynand Steyn. The title of his lecture is Minding and Mending Our Ways. With that, I'm now pleased and privileged to welcome the Vice Principal Research and Innovation, Vice Principal Research, Innovation, Postgraduate Education, Professor Sunil Maharaj, to the podium to formally open this prestigious event and to introduce Professor Steyn. Prof Maharaj.
Good evening, colleagues. I know we didn't have cocktails yet, but good evening. Welcome, wonderful to have all of you here. I'm not sure if Professor Steyn asked you guys to attend, so part of the performance management. But Professor Steyn, the person who's presenting our inaugural address today, our Vice Chancellor and Principal, Professor Francis Peterson, members of the executive that are here, deans, directors, professors, heads of departments, chairs of schools, welcome. Wonderful having all of you here this evening. Certainly a special welcome to Anita Steyn, wife of Professor Wynand Steyn, and his children here, Wynand, Junior, Vikas, and Yolanda. Welcome. Thank you for making time to support your dad. Also welcome Mom, Ms. Audrey Steyn. Wonderful to have you. And mother-in-law, Ms. Lana Bota. Also welcome to Professor Wynand Steyn's family, brothers, sisters, and brother-in-laws and sister-in-laws. Wonderful to come and support family. And I'd also like to welcome one of the special friend of the family, Professor Peter Estek. Welcome, sir. Also colleagues, students, ladies and gentlemen. A warm word of welcome to each one of you on behalf of the University of Pretoria. I always look forward to an inaugural address by one of our professors. It is a celebration of a colleague having progressed to the highest academic rank and an opportunity to be addressed by top scholars on the latest research in their field. This is an opportunity for our professors to give us a glimpse of their thought leadership and us as the audience to broaden our horizons. The University of Pretoria makes a difference in countless ways, but at least in the heart of it, our impact are the graduates we deliver and the impactful research we produce. Both of these are fully dependent on the kind of scholars the university attracts and nurtures. As our most highly esteemed faculty members and experts in their field, our corps of professors is the vital link for enabling the manifestation of the university's ideals within the academic departments. They also drive our engagement with the external environment through collaboration with their peers, both locally and internationally, but also with government and industry partners and others. Often, an inaugural address presents research that has just been or not yet published, and so one is given a glimpse into the future, sometimes in a field of interest vastly different from one's own, ranging across topics such as cultivation of potatoes to music therapy and everything in between. This evening, however, I have the honor of introducing a colleague, a fellow engineer, and moreover, the Dean of the Faculty of Engineering, Built Environment and Information Technology, and indeed a privilege for me to have been allocated to officiate at this occasion. Ladies and gentlemen, on many occasions I have heard Professor Steyn speak. He always took care to emphasize the human face of engineering. From the abstract he provided for his address this evening, this is again apparent under the evocative title, I quote, "Minding and Mending Our Ways," close quote. He paints a picture of roads not as mere infrastructure, but as connectors that are an essential part of our social fabric and, of course, survival. By doing so, Professor Steyn, you foreground the societal impact of your research, something that is of cardinal importance for us as a university. After all, as is stated in our UP vision, making a difference is part of what we want to be known for as an African global university. Your abstract also clearly positions your research topic as part of a collaborative, transdisciplinary endeavor, bringing together physics, material science, and engineering, and impacting almost every conceivable aspect of society, such as education, healthcare, trade, and security. As a university, we have long believed that solutions to the most vexing problems facing humanity will only be found through research collaboration beyond the traditional boundaries and experts across the globe working collaboratively. Ladies and gentlemen, having spent the last 35 years studying, as Professor Steyn puts it, I quote, "the intricate dance between vehicle ties and road," close quote, Professor Steyn is the right person to give us a glimpse into the complexities and interlinkages that characterize the field of road engineering. Perhaps counterintuitively, it is a field that is growing of importance as Society 5.0 becomes a reality. On that note, Professor Steyn, I'm also interested in hearing you share with us the latest developments around automated monitoring and maintenance to ensure sustainable transportation practices. Ladies and gentlemen, I think you'll agree with me that there is every indication that we can look forward to a more stimulating and interesting address by Professor Steyn this evening. However, it is my pleasure to introduce him to you. Professor Steyn is the Dean of the Faculty of Engineering, Built Environment and IT at the University of Pretoria. Prior to this role, he was the chair of the School of Engineering and the head of Department of Civil Engineering, where he held a full professorship specializing in road pavement engineering. Professor Steyn as HOD played a pivotal role in the development of the university's state-of-the-art Engineering 4.0 facility, which was officially opened in 2020. Situated on the Innovation Africa at UP Hillcrest campus, the facility, which is a collaboration with the South African National Roads Agency, or SANRAL, the Council for Scientific and Industrial Research, which we call CSIR, and of course the entity, which is the entity of the Department of Science and Innovation. It focuses on research on smart transportation, cities and infrastructure. Professor Steyn is a professionally registered pavement engineer with a research interest in vehicle-pavement interaction, accelerated pavement testing, pavement engineering, pavement materials, civiltronics, and instrumentation. He completed his undergraduate and postgraduate studies here at the University of Pretoria. He has co-authored and edited something like 57 journal papers, 23 book chapters, and 117 conference papers. He is an associate editor of the International Journal for Pavement Engineering and the International Journal of Pavement Research and Technology. He has a B3 NRF National Research Foundation rating. He is a fellow of the South African Institute of Civil Engineers, a fellow of the South African Academy of Engineering, and a registered professional engineer with the Engineering Council of South Africa. Ladies and gentlemen, please join me in welcoming Professor Steyn to the podium.
Thank you very much, Bridget. Good evening, ladies and gentlemen. It's indeed a privilege to be here tonight. And I appreciate Prof Sunil, Prof James, Prof Peterson, Prof Loretta, my fellow deans. They sit there in the back. It's one of the best groups to be part of at this university. My colleagues from the departments, the faculty, as well as other faculties, I really appreciate the fact that you made the time to be here tonight. And then also, obviously, my family, all of them that can be here, friends. It's indeed a privilege to do a presentation like this. So, as Sunil has indicated, the topic is minding and mending your ways. Now, I've learned over many years of lecturing that there's one thing that makes students focus. And they also always want to ask you, so is this in the exam? So, and then they focus, and if it's not in the exam, there are other important things. So, I decided to start with the exam summary. Then, hopefully, it will assist everybody to focus. So, the exam summary for tonight is straightforward, easy to remember, each other matters. As we talk about the vehicles, the pavements, the interactions, that's a day-to-day occurrence in our lives. Any story starts somewhere, and all of us has got many stories. So one specific story for tonight as background and introduction is one that started on a Wednesday afternoon in 1985, obviously on a road between Potchefstroom and Western area. And during that trip, there was a program on the radio talking to, at that stage we would still call school children, learners these days, I suppose, about careers. And they spoke about civil engineering. And then, in a different time, I took out my phone and Googled, or we got home and I got hold of an encyclopedia and looked for what's a civil engineer and started to look, and this sounded like something really cool to do. And the importance of that one little part for us today is the power of actually marketing what we are doing. Because honestly, if I did not hear the marketing on the radio, which was a very good talk about civil engineering, I would not have known about it. So for sure, in terms of marketing, what we are doing, why it's important, what the impacts are, extremely important, in my story at least. That was followed with a later trip in 1985, this time from Western area to Pretoria, to go to the first of two what I call career molding institutions. And this was the CSIR, and very specifically a bursary interview at what was then formerly called the National Institute for Transport and Road Research. Those days we still wrote everything out in detail. And I had the privilege on that day, apart from testing and various things and so on, that they actually allocated a few of the staff members to have a discussion with me. And this is where one has to learn the lesson that when you meet people, you must be careful because they may become part of your life for the rest of your life. So the mentors that I met there that day include, and I've cut out the surnames because I know who they are. If I start at the back, Henny and Wessel and Alex and Chris and Emil and Morris and Frank. And very importantly, and you'll see at the end why, Gerrit Jordan. He was the guy which had the, not necessarily privilege, to keep a matric learner busy for an hour that day in a discussion of what's pavement engineering, what's research and so on. And after that day in 1985, the rest of my career, Gerrit has always been there in some way. And the current work that we are busy with on nanosaline stabilization of materials is the main driving force for that. So make sure that your first impressions are not lost. The second of the career molding institutions is when I traveled in the beginning of 1986 to the University of Pretoria to start my studies over here. And between those two institutions, I must be honest, there's various others that played a role, but in terms of career molding, major work done by colleagues and friends and mentors in these institutions, as well as the numerous opportunities that was provided by them. And before we move to the technical part, another small important part that we have to remember. I would not have been in matric in 1985 and at university in 1986 if it wasn't for Laerskool Gerrit Maritz and Hoërskool Western Area. Because we have to realize when we get the students, they can mostly read and write and do maths and so on. So there's a major job in our basic education to be done very well before we can take on students and carry on with them. So that the short story. Now to some technical stuff. And I realize we've got a range of backgrounds and knowledge and specialities over here. So a bit of pavement 101 or how to read a road. It's important to realize we always complain about our roads because it's something nice to complain about. But we've got the 11th longest road network in the world. So you can see the stats over there. And this road network is about 20% of that is paved. Now in engineering, pavement engineering terminology, paved means it's either got a blacktop or a concrete surface. And the other 80% of those roads in South Africa are gravel roads. Gravel roads that are designed mostly, not necessarily always maintained well, but it's also designed pavements. So we've got a vast network, 750,000 odd kilometers of roads, linking communities, schools, jobs, everything that we travel on a day-to-day basis. So we've got a significant asset to look after. A bit more on pavement 101. So a road pavement, if we talk about that, just to clarify, pavement is not a sidewalk, not for a pavement engineer. It's a very specific designed combination of various materials. And I'll get to the materials just now, that you have to look at things like the traffic, because obviously that's why we design pavements, to carry the traffic. So if I look at traffic, materials, environment, and the structure is how we combine it, the materials is the one part over which we've got the most say and control at the start. Because the environment, that's what you get. And I'll show you a slide on that a bit later. You have to understand the environment and work with the environment. The traffic, you've got a bit of control about. It depends on what type of road you design. It depends on how you regulate your traffic. But you've got a bit of a handle. But the materials is really the part that's the interesting part, where if it's granular materials, to keep it simple, it's affected by moisture content. If it is bituminous materials, it's affected by temperature and loading types and speeds. I'll keep to the temperature for tonight, because that's a major effect in terms of our vehicle-pavement interaction and the basic understanding of how complex the system is that we place our traffic on, and that has to carry on doing its job for 10 years, 20 years, some of them 30, 40 years out there, carrying us to the destinations that we are looking at. Now, we can also look at the way that pavements operate as structural or functional. Structural is a bit more the stresses and strains type of things like what Prof James is much more interested. Functional is that part that we as the road users experience mostly. And that's why with this discussion on thinking about our roads, vehicle-pavement interaction, something that all of us can appreciate and plays a major role in our lives, the focus will be on the functional performance of roads. Another important concept is to understand how we design for traffic. Obviously, if you go out there, you see different types of trucks and buses and cars and bicycles, and you have to have something to design for. So in pavement engineering, we use what's called a standard axle, or an equivalent 80 kilonewton axle. So there needs to be a bit of equation somewhere. I try to keep them small. The importance of this equation, and the reason why I want to highlight it, is the fact that we take vehicles, and an 80 kilonewton axle is basically just an axle on a vehicle weighing 8 tons, in very simplified terms. That's what we design for. So we look at a small truck, may have 2 of these axles, and a large truck may have 10 or 12 or so on. Then we calculate, we determine how long this road should be there. We've got traffic engineers and transportation engineers that assist us with understanding the traffic into the future. And now you can start to understand how difficult this thing would become, because I need to have an assumption of what the trucks will look like and how many of them will run on a certain road in 10, 15, 20 years' time. But then we convert all of that to a total number of standard 80 kilonewton axles. And that's what we design for. The problem with pavement materials in general is if we look at the loads on these axles, so it's quite easy to say if I've got an 8-ton axle and I increase the load by 10%, then I can carry 8,800 kilograms on it. And it sounds like a good idea, because I mean it means I need less vehicles. The problem is that pavements in general, the damage of a pavement is following what we call an exponential relationship, which means that if I overload my axle by 10%, which is not much, the additional damage to that road will be 46%. If I go up to 20%, which is still not bad, I will do 107% additional damage to that pavement. And that's where overloading becomes a real problem, because now you design a road for 30 million standard axles over a 20-year lifetime, if all of the axles are legally loaded. But the moment people start to overload those axles, you actually consume that pavement much quicker than what you should be doing. This tire story becomes more complicated. So if you normally just kick the tires and buy a few new ones, it's much more interesting than that. This is a concept that is based on a development of a colleague of ours, Maris de Beer at the CSIR, which is a tire contact stress measurement device. And the two pictures that you see over there, just for clarity, that's a dual set of tires. So that's one tire, one tire, one tire, one tire. So it's half an axle. And those pictures indicate to us what the contact stresses, what is felt between the tire and the pavement surface. If on the left-hand side you are slightly overinflated on the tire, or on the right-hand side when that tire is overloaded. Now you can see, you don't need much engineering to see that that overloaded condition has got severe implications for our road. And the two pictures below is tests that we've done with the HVS, where you can see if you apply that type of loading consistently, you actually see it in the shape. And if you apply that one, you can actually also see that in the shape of how your pavement surfacing deteriorates. So there's a direct importance in terms of the tires and the inflation pressures and the size of the tires on what happens to your road. And obviously the load that you apply to these tires. And then just as a little additional curveball, then you are used to tires with a certain type of rubber that's manufactured in a certain place, and then you can't get them anymore, then you start to import tires, and the type of rubber changes, and therefore the contact stress changes, and you've got no idea what's going to happen in 10 and 20 years' time. So let's try to keep where we are. So when we start to get to how to read a road, what I mean with that is the ability for a pavement engineer. You cannot always have the full design, the full details and so on, but you have to evaluate the road, look at the road condition and determine what is the condition of this road before I do all of the measurements. So we've got standard type of graphs similar to this one. This is one example that I took that indicates to us that as we use a road, as any other infrastructure, the road will deteriorate. The materials will change properties, it will deteriorate, the load will do stuff, the environment will do stuff. So we've got an expectation for different types of road structures. If you look at them, this type of road should start to show some rutting halfway through their life. That one should start to show some cracking at some stage in its life. And based on that understanding, you can have a look at the road and then determine this road is actually in a good condition, although if you don't understand the background, it looks a bit sort of, it needs attention. Or another road that starts to show a type of crack that should not be there is actually in more trouble than what people would think about. So to explain this in a bit more detail, this is a typical postgraduate exam question for my pavement design students. To say, listen guys and ladies, that's an image. Tell me what's the story of this road. And to have a look at this one, for instance, and I've used the pointer, if you start to look at it, you'll see the vegetation and stuff is really next to the road. There's no road reserve for fences and stuff, which should start to make you think, apart from other reasons, that it may not be a normal provincial road or a town road. It may be a nature reserve or something like that. There is a bit of a hint on that. But then if you focus a bit more and you understand where we use certain types of surfacings and materials, you will see that this type of surfacing is what we typically call a sand seal, which is a very light type of seal. That ticks another box that it's probably in a game reserve because they often use them. And then you will start to put the picture together. And the picture in this, to summarize it, is there's a lot of vegetation over there. It's dead. So it's not summer season. This is the dry season. Why is it important to know that it's a dry season? Because if you look down here, there's some cracking. But the cracking is close to the edge of the road. So most probably that type of cracking was developing as you had rainfall, gets to the vegetation, some on the side of the road, it weakens it a bit. So those cracks that you see over there is most probably not caused by traffic. Another little box to tick, if it's in a game reserve, you most probably don't have large trucks on this road. That's why you don't see too much rutting and so on. And then lastly, if you focus well, you'll see that the warthog looks pretty happy and pretty well fed, so it's probably an area that got lots of rain in the last year. So the fact that this road actually does not look in a bad condition means that it's in a very good condition for its purpose. And for its purpose is very important in this case because we construct roads, design roads for different purposes. And if I focus just on two major ones, the one is mobility and the other one is accessibility. So mobility is the N1, not on a Monday morning. That's to get from point 1 to point 2 as quickly as possible. That's a type of pavement structure that we design. Wider lanes, more lanes, we try to get the traffic mobile. Accessibility, on the other hand, is when you've got a small little rural township and you need a way for the people, the community, to get to the closest school or police station or hospital, clinic, whatever the case may be, and you design a different type of pavement structure for that because you don't have trucks on that, you don't have buses on that, so you can design totally differently, you can make different assumptions on that road. You need to understand what you are designing for, what you need to maintain for, and what you are trying to do in this big picture. So, in terms of minding our ways, I would like to focus on the observation and what does this mean for us. Minding the roads, observing them, checking, quantifying, getting data from the road, listening to the road. Because if your ears are good, you can hear the roads are talking to you. And that's on any given day if you focus. So, vehicle pavement interaction, riding quality, what does that mean? If we look at trucks and roads, and this is a very complicated way to show you that a vehicle pavement interaction consists of a vehicle with dimensions, with different loads. Below that there are suspension systems that can be various types of ones. Then you've got tires, the tires have got certain suspension. That runs on a road surface. And that road surface is never completely level and flat. The best that you can do will still always have a bit of unevenness on that road surface because you build it with big machines and so on. So you attempt to get it as good as possible because the more smooth that road is on day one, the longer the life of the road will be and the less your interaction will affect the condition of your roads. So now to complicate the picture, and that's why I showed you the contact stresses and the load effects and the overload effects. This is what happens on a real road. So if you look over here, this is the loads. That blue line over there is, if I assume, take this 80 kilonewton axle, 4 tires on it, so it's 20 kilonewton per tire, basic maths. So that's if I assume and I don't understand how a road works. What happens if my vehicles actually travel on that road and there's interaction and they start to bump up and down? You start to get a condition where a vehicle can be totally legally loaded, but it applies overloaded conditions at certain spots on that road. And you have to take this into consideration in your design and your maintenance, because otherwise that road will fail prematurely, not because anybody did anything illegal in terms of overloading, but just because the road is uneven. Get back to my exam point, each other matters. The road is uneven, the track will generate more dynamic loads, and it is a slightly vicious circle. To complicate matters a bit further, and I thought this will happen earlier this afternoon, now I think it will be later this evening, we'll have thunderstorms in Gauteng on a summer afternoon, because typically it gets very hot, and the rain comes, and 30 minutes later it's cooled down and life is good. Just to show you why that is a headache for a pavement engineer. This is temperature data that we measured just outside Engineering 4 a year or two ago. So that's temperature over there. The orange line is the asphalt temperature and the blue line is the air temperature. And that's sort of a diurnal cycle. That is 9:30 in the one morning, that's about 9:30 the next morning, so that's 2 days. That's the afternoon at about 3 o'clock. At about 3 o'clock, this road had a surface temperature of about 47 degrees Celsius, which is not too much for an asphalt road in Gauteng. They can get warmer than that. And what happened then? There was a thunderstorm. The thunderstorm was typically 20-30 minutes, cooled down everything very nicely. What happened to my asphalt? This is a parameter that we call our asphalt modulus, or the stiffness, or if I can translate it like this, this indicates how soft or hard the asphalt is. Now, the softer my asphalt is, the quicker it's going to flow, the quicker it develops things like rutting. The harder the asphalt is, the easier it is to start to become brittle and develop cracks. So I have, within 20 minutes or half an hour, I changed from a relatively low stiffness to a relatively high stiffness for this specific asphalt mix, which should add to indicate to you that apart from the fact that the unevenness on the road makes my tires bump up and down and therefore change the dynamic loads consistently, the material itself is actually changing properties also consistently, which is in the undergraduate explanation for this. So the undergraduate explanation of asphalt, because it's a complicated concept, is a fizzer. Because all of you know a fizzer, and this is exactly, bitumen and fizzers are the same. They are viscous, temperature sensitive materials. If you put a fizzer in the sun, you can stretch it out forever. You can mold it, like bitumen. If you put it in the fridge and you take it, you break it, because fatigue happens. So there are ways and means to keep students interested in the topic. Now, if you look at this concept further on, so now I design my road, and over time, my roughness of the road increases, so the roughness deteriorates as the track runs on the road and develops more roughness. My static load on my truck, that which I load it to, that remains pretty standard over the life of that road. However, as the roughness increases, this dynamic component starts to increase. And I can solve part of that with better suspension on a specific truck and so on. But at some point, I need to do some maintenance on my road. I need to get it in a better condition again. And that's the only way to get rid of that unintended dynamic load effects. Now, a very specific practical example of this was when we did about 15 years ago bridge deck joint inspections in KwaZulu-Natal on the N3. So big trucks running on the N3 on a bridge, and the bridge deck joint is just this little device that we put between the rigid bridge and the rest of the pavement to make space for expansion and so on. So we inspected this, and then being a pavement engineer, I did not only look at the bridge, but downstream, so the traffic run in that way, you will see there are 3 very isolated bad spots on that road that was really damaged. Now, if this was due to general overloading, you would have expected that all of this had some fatigue cracking and so on. So at that stage, we started to do a bit of analysis. And this is 15 years ago animation for the young ones, it was possible. And this is what happens. That bridge deck joint actually stuck out just a small bit on top of the surfacing. And you've all experienced it. You get to a bridge and it's almost as if there's a bit of a bump. And when we did the analysis on this, we saw the typical body bounce axle hop behavior. And this caused the load to have a potential 12% overload and about 57% increase in damage at that spot. Again, not the fault of the trucker at all. This is the condition of the road. And interestingly, if we look at a better installation of that joint and make sure that it doesn't stand up so much, 30% less damage on the road. Just by understanding, listening to what the road shows you, tells you, and reacting to that. And not just the textbook, but go out there and see what the field tells us. So to summarize this, and this riding quality vehicle interaction type of phenomenon, and I don't have time to go into all the details of these, but as an indication, we spoke about increased road loads now. Why is that important? Because increase the damage, the maintenance cost, and we've got an environmental cost after that. It increases fuel consumption. A bad road needs more fuel to travel on that. It's again, bad for operating costs, bad for the environment. It increases your vehicle damage. And all of you will know that if you drive in a really bad vehicle, you start to get damage on that vehicle. Increases your logistics costs. And very importantly, a part that some very interesting work we've done, it starts to damage your transported cargo. And that means that your logistic cost goes up, you start to get damage on stuff that you transport, and obviously that's written off. You can't get it back. So what did we do? Some of the nice, interesting applications of this in real life. So the first one was with ZZ2 that produces a lot of tomatoes and avocados, and they had this problem. They've got a huge gravel road network. And they need to maintain this network because it's their own network. And the way that you maintain a network like that is you get a grader and you come and grade the road and you get rid of the corrugations and so on. But it cost them quite a lot of money because they have to grade everything. They did not know which part was bad and which part was not bad. So we developed a little system where these little sensors were fixed to their vehicles, and after traveling over their roads, you could get this type of map every time that the vehicle traveled over a road, indicating to you that on this specific section of road, all of that sections has got a riding quality that's acceptable for their conditions, but those spots over there, they are bad, go and fix them, only them, and don't spend too much time on the diesel and the processes. By doing this in that specific year, they saved between 40 and 60% on blading their roads. What's the benefit of this? It means it's a saving on your bottom line because it's something you don't have to do anymore. Why are they interested in this? Why should a tomato farmer be interested except for the blading cost? And that was the next very interesting part. And now I've got 3 past students over here, which fortunately all of them could be here. And they did a major lot of this work. So the first one is the work that Linky Pretorius did in terms of what's the damage that happens to those tomatoes when you transport them. So it's great fun. We had these pressure-sensitive mats that we placed in between the tomatoes, large crates of tomatoes from the field, 2 small trucks, 2 large trucks, measured all of this, and so what? The so what was that as a tomato producer, you want to sell the best tomatoes, obviously, because then you get the best price, you get the best profit. How do you measure whether a tomato is good or not? You look at the shelf life. So typically shelf life of a tomato is 10 days, and the model that she developed from this indicates, and this is just one of them for one of the colors of tomatoes that also plays a role, as the roughness of the road gets worse, increases, the shelf life of your tomatoes drop. And it makes sense. All of you have seen people going to the vegetable store and they take the tomatoes and want to see if it's fresh and just sort of feel if they are good. Now if you keep on feeling if they are good long enough, you start to bruise them. And that's what the model says. If you fix the road, get the road to a good quality, you can extend the shelf life of the tomatoes, which means that more tomatoes are sold. So with that links to work that Andre Broekman has done. Because then we started to realize, okay, this is cool to understand what does a tomato feel like in a truck. But you really wanted to integrate it a bit more. So based on his master's work where he developed this sensitive clippy ballast, we developed the smart avocado and the smart tomato, which put the sensor right inside this printed exoskeleton so that we can actually put it together with tomatoes or avocados or whatever we are transporting and really see what they feel. Because otherwise you stand outside and you do all these models, but you don't really know whether your model is calibrated. So that was one part over there. The other part, and this was work that was done by Elizabeth Wessels, is you want to preferably be able to continuously measure this condition of the road. The mining part of the road, continuously, not send the truck out once a year to get an indication. So she was at that stage linked to the company Tracker that has these devices that actually tracks your vehicle. But the interesting part to that is this device also has got an accelerometer. So we realized that if you are able to get into the inside and the software of this device, you actually have got a whole range of potential measurements that can tell you what your different vehicles feel on the road when they travel. So it's not only looking for your vehicle when it's gone, but also asking your vehicle how it experiences the road. And this gave rise to the whole idea of vehicle telematics crowdsourcing. Before crowdsourcing was a popular term, because now you can have a large community of vehicles that reports all this data, and from this community of data you can start to understand all the vehicles indicate there's something wrong over there. And with a road, it's like this. I don't necessarily need to know exactly this is wrong at that exact point. Number one, I need to know that my vehicle starts to react in a certain way, send somebody out to just go and have a look at that and fix that problem. And I'll get back to this one in the last slides because it's actually quite interesting how humans and peoples now start to affect technology in this way. So, halfway through, minding to mending. So minding focused on we need better roads, less dynamic loads, less damage, better products. Better products is higher profit. Prof Sunil mentioned it's sort of looking at the big picture. If a tomato farmer can get better profit for their tomatoes, it means they pay more tax, it means they can employ more people. So your unemployment can be linked to how good or bad your roads are. Because if you get a bad price for your tomatoes, you get less income, pay less tax, you can employ less people. Or the version for the students was that the condition of the road affects the price of your beer, because logistics matter. The second part, a few slides, now looks at mending. Now that we know that there's something wrong with the road, how do we fix this? What can we do to fix our road? And I would like to just focus on a few of those points. Firstly, just for context again, if we look at the road pavement and the gravel aggregate, the gravel that we use for that, depending on a few assumptions, you need about 1,100 thereabouts cubic meters of material per layer per kilometer. Now for context, that's about the material filling the Senate Hall. That's a huge lot of material for one layer of possibly 3, 4, 5 layers of that road for 1 kilometer of a 200 kilometer road. So material is a bit of an issue if you have to import it. Water, and this is again sort of a general, sometimes less, sometimes more, but you need in the range of 150,000 liters of water per layer or per kilometer. It's a huge lot of water in a country where we don't have water. And the unfortunate part is you speak to Frank, you need good water. You don't need the stuff with the salt and stuff in, because then you've got other problems. So that is quite a problem. Now for years, as pavement engineers, we looked for good materials. And we always had to think about marginal materials. And marginal materials was typically the type of material that does not qualify to really be used in the road, because there are some of the properties that's not acceptable. And mostly things like the clay content. The problem with clay is that you've got these very, very small clay platelets. When you've got water into your clay, it starts to swell. When the water is gone, it starts to shrink again, and it causes major damage on infrastructure. Also, since 30, 40 years ago, you now need a mining license to get new material out of the earth, and that's a major issue. So you would like to make more use of available material as far as possible when you start to fix your roads. A very important aspect in this part, people often complain, they say, oh yeah, the roads just deteriorate. You know, all matter deteriorates over time. The roads do, the cars do, the buildings do, as bodies deteriorate over time. That's just a matter of fact. We have to manage it. We have to understand how it's happening and then see how can we manage it over time to extend good life as far as possible. And these environmentally induced effects is a major problem there. Things like the sun. You cannot put a cover on all your roads to prevent your asphalt to become dry. So you have to design for that. And apparently, the standard engineering solution of duct tape is not acceptable. Some people take exception to that. Okay, so in terms of our maintenance and rehabilitation, what we then need to do is you need to understand your materials, your traffic, your environment, and then you start to develop some type of maintenance program. And maintenance can be anything from, let's run this road until we need to do major structural rehabilitation, or on the other hand, let's do more often resurfacing, smaller work on this road, and actually keep on keeping it in a good condition. And most of these options are okay if you plan and budget for that. The interesting part to it, and this is a standard outcome of international research, is that as with anything in life, the quicker you make a plan, the better. So if you look at the standard sort of life of a road, accumulated axle loads, years or so on, then typically if you start with a very good pavement condition, it takes about 75% of the time for a 40% drop in your condition to get 40% worse. The problem is the next 40% takes about 17% of the total time. And yes, it's general, depends on what type of pavement and so on. But it means that if you do not attend to this road at the right point, where it costs you 1 unit of currency for rehabilitation, and you leave it for that additional 17% of time, you are going to pay 4 to 5 times to fix exactly the same infrastructure that you could have done at a lower price. And this is one of the real tragedies, not only in South Africa, I must emphasize that also, lack of maintenance budget is an international road infrastructure problem. It's better in some countries than others, but if we can spend small amounts earlier and can get that message through, our general infrastructure would be so much better. Then in terms of these marginal materials, and this is very specifically where the work with Gerrit comes in, we started to realize over the last number of years there are various other ways to treat our clay materials. And a very specific opportunity came to use what's called nanosilanes. Now I will not go into the chemistry. I realized why I had to do chemistry and engineering when we started to do this work. Because suddenly a lot of things around valence bonds and things like that suddenly made a lot of sense, because I realized why it's important. The important part to understand is that treating your granular marginal materials, which has got clay content and so on, with some of your nanosilanes, you can get to the point that you can make them hydrophobic, which means that water does not affect this marginal material as much as it would have been before. And this leads to the benefit that you can actually now use in situ local material. You don't have to cart material in. Lower quality material, but you can treat it to actually operate at the same level than your high quality material. And just recently, as you see there, January 2024, a team supported by Inaugural, and they sponsor a huge lot of research in this country, finished what was the first draft of upgrading of unpaved roads. A really major document, part of the technical recommendations for highway series, of which, again, I told you, we meet each other again, myself and Gerrit and the other colleagues, Full-Page Green and Gerrie van Zyl. These are all guys, old padmakers. And just by the way, padmakers I think is the English term also. I don't think there's an Afrikaans term for padmakers. But where all of them contributed to actually look at what's the cost of upgrading gravel roads in South Africa, because there's a huge cost if you'd use the traditional ways. But if you start to look at where you can intelligently use new materials like your nanosilanes, you can actually make a major saving. Why do you want to save on your road construction and maintenance cost? Because it means you can do so much more. Instead of doing 1 kilometer of road, you do 2 kilometers of road. Instead of doing 1 township, you do 2 townships. And also, the benefit of that becomes that suddenly you look at different types of applications, like hydrophobic surfacings for your roads. Because the moment you can do that regular maintenance, you remember the 40% and the 1 to 4 indication over there, if you can have a team of local labor that can do a good job with a hydrophobic surfacing regularly enough, you extend the life of your pavement significantly. And that's a major part of the current implementation. The TRH document is now in its draft format for 2 years to see how it works in practice, before hopefully it's going to make a major difference on road building cost and upgrading cost and maintenance cost in Southern Africa. Lastly, a few thoughts about foresight, alternative futures, what's important, what would we need to look at. I think it's safe to say that we will probably need to use roads for a while still. The auto drone type of traveling and so on may be in the news, but we will use vehicles for a while. There's changes in our materials, there's shortages of bitumen, there are new materials like our nanosilanes and so on, so we need to understand and listen to our infrastructure in a better way to apply these new ways of doing it. And that's where something like smart digital twins comes in. A digital twin is just a model that we develop of something, but it can be interactively studied and analyzed and managed. And what's quite important, the digital twin continuously gets new data in. So it's not just a model that I developed and it's there and I do my modeling and I don't understand how this pavement is actually alive. So we are doing quite a bit of work on that, starting to collect huge sets of data And the only thing that you should see from that is, that's confusing. Some of it is red, some of it is green. How do I decide what I do over there? Where? Because roads have always communicated to us. This modern thing about smart infrastructure, smart roads, smart so on, they did not suddenly become smart. They always spoke to us if we knew what they were saying. We knew how to look at the cracks. But the problem with the human mind is we tend to focus on something. And that's the way that our brain developed. We have to look at, if there's a lion chasing me, I focus on the lion. I don't look at the beautiful flowers and stuff. So if you see a pothole on the road, it's easy to miss the cracking, the rutting, the vegetation and stuff. And that's where, in terms of this putting together automation, machine learning, crowdsourcing, to actually assist us to start to highlight where are the real problems. We've got very strong programs in terms of that. It starts to allow you to do things like this, where your vehicles, with their sensors, travel on the road. They start to tell your system autonomously where are the bad spots. Your system tells your maintenance team, and your maintenance team can immediately go out, solve the problem where the problem is. The bottom line, decreased vehicle operating costs, increased life. Another part is focusing on the improved minding. And this is where continuous sensors in pavements is a very hot topic currently internationally. We also in the Inaugural research had a look at some of that. The problem with continuous sensors in a pavement is how many do you need? And where do you place them? And how do you get electricity for them? And how do you maintain them? So there's a few challenges still. That's why the continuous sensors in vehicles is actually a much easier way to go, because the vehicles travel in any case. They've got batteries in any case. Most people will have their telematics. They're in any case worried about their vehicle being stolen, so having the sensor there is a benefit. In this regard, we just started with the MIT program at UP, two projects looking at using dashcam footage, videos, through a machine learning system to actually collect all of this data and say, listen, at this spot on this road, there's something wrong. There's probably a pothole, there's probably a crack, there's probably some rutting happening. Now, this is where humans become interesting, because this is where ethics and privacy and Society 5 becomes an issue. Because everybody doesn't necessarily want anybody else to know where they travel today, for whatever reason. I mean, it doesn't have to be bad reasons. But this is where that challenge, technically we can do this today without a problem. We can put it in all vehicles in the country, we can get all this data. But ethically and from a privacy viewpoint, a major concern to look at that part. And that's why where we move from fourth industrial revolution to what's called Society 5, where we look at the interaction with humans also. In terms of improved mending, trying to get to the point where we can immediately and continuously mend when there's a problem. Do not wait until we've got major rehabilitation and maintenance to do. Come and fix a crack long before it becomes a major issue. And looking at these improved materials, the relatively low-cost materials that can actually extend our road network significantly. With that, some conclusions. And the conclusions, I thought, some of it is slightly more technical, but all of them hopefully to such an extent that we can learn something from it. So, how to human is a topic that we are using in EBIT often these days, because we are very good at technology. But sometimes we sort of forget that there's communities and humanity. So, first important point, and this is a big word that I learned recently. Why do we do this? Why are we interested in developing better ways and new ways? And I'm talking about pavements now. My colleagues talk about saving water and saving plants and all of those things. And the nice big word is transgenerational empathy. Or it can be translated as being a better ancestor. So try to make sure that the roads that your grandchildren travel on in 20, 30 years is hopefully still the roads that you constructed and maintained and did a good job of. Because if it's not the case, then it's more cost that needs to be covered in the meantime. So that's the first one. Then, think about this and remember it. And this is why it's going in various directions. When you are on the road, try to be as smooth as possible. Because if you become rough, you start to generate dynamic loads in the trucks. And those dynamic loads gets back to you and it makes you rougher. So if you are on the road, try to be smooth. If you are the truck, try to soften your suspension or lower your tire inflation pressure slightly. Because yes, you can have the best suspension for your truck with the best optimal inflation pressure. If that's not working well with that specific road, you start to damage the road. And the road is starting to damage you as a truck again. When you're the tomato, just enjoy the ride and bring joy. And this is important because, why is the tomato important? Because that's what society is all about. We need to eat. If a farmer produces the best tomatoes that they can, and the consumer get them in a bad quality, that's not good. So try to be the best tomato that you can be. And then, and this is very specifically for us as engineers and technologists and so on, to realize that sometimes, and this afternoon I added the probably always, because you can never be totally sure, but it's not just the data. The data is beautiful, the data are wonderful to collect, the mathematics is wonderful, but we have to keep in mind that all of this is done to support communities, not for the technology. It's wow, the patents, the papers, all of those things, but it's there to have somebody buy a very good quality tomato, enjoy it, and somebody got a job because you were able to buy that good tomato. With that, some thanks. So firstly, I would like to thank what I would call my professional village, coming from the term that it takes a village to raise a child and probably an engineer also. And my professional village consists of various, and there's really, we'll keep on for another hour or two, people in this industry and institutional colleagues and friends and funders. And this goes wider than South Africa, and it's each and every of those companies and entities that puts money into research and development. So important because then we can solve problems. The next ones are my family. Now, I was extremely privileged to know at least two of my grandparents for quite a number of years. And they made it quite clear that you need to be inquisitive. You need to read, you need to understand, which made quite a bit of a difference. Also, my parents, and I'm privileged to have my mother here tonight, they also made it clear that, listen, there's no way to stop. You read, you study, you enjoy, and you make sure that you get these things covered. So I'm really privileged for that. And then also, parents-in-law, because I know my parents-in-law currently longer than I don't know them. And I'm again fortunate to have my mother-in-law here tonight. And they also totally supported stuff that I think you guys don't always understand. They sometimes look at me if I tell them stuff and that's cool, it's good, yeah. But thanks for that. Then also, my siblings, and I indicated siblings of all kinds, because it's my brother, my sister, my brothers-in-law, my sisters-in-law, because for them also, it's always a joy to discuss things with them on various other technical fields also, as well as my friends, the ones supporting, trying to understand what we are doing. And then that little sentence just shows you that if you know, you know. If you don't know, you don't know. I would like to thank my good wife, Anita. And it's good to have her here because, I mean, we know each other for much, much, much longer than we don't know each other. And she's the one who supports this and listens to it, and I think more often say, yeah, that's a cool idea, let's see. And but supporting when I'm traveling, when I'm working, all of these things, major thanks for that. Together with that, my two sons, Wynand and Wikus, who had the privilege at a very young age to be 2 o'clock in the morning at the Johannesburg Fresh Fruit Market because I needed to pick up sensors. And they sort of enjoyed it in that way. Really wonderful to have you guys and your support. And then Yolanda, my third child, which I don't know that long, but long enough. Also for being inquisitive and understanding. And then the last two, the one can't be here because she would have taken over the lecture. She's quite good with that, Lana. And then Wynand, that's also here, and I'm pretty certain he will remember something of this. So that's why I tried to get it into sequence, guys, but the sentence didn't work out. So if you focus a bit, you will understand what the letters means. And then lastly, my absolute joy and thank for talents, health, blessings, and opportunities that all work together over a long life and a long career, and that I can always feel blessed in terms of the things that's possible in my life, for which I'm totally grateful. Lastly, I told you, you need to remember the exact tip. Each other matters. I hope you remember that. Thank you very much.
Yes, minding and mending our ways. Good thing about Wynand, who maybe I need to say, I've known him for almost 20 years now. I've worked with him since I moved to South Africa, and I still work with him. He's got very special ways of making technical and non-technical people feel that they understand what he's talking about. And thank you for that. And I've got that special role of summarizing in very few minutes what Wynand has said. So Wynand, in your lecture this evening, you highlighted the crucial importance of data in designing, maintaining, and improving our roads. You made it very clear that the condition, whether bad or good, of our roads has a direct bearing on both the quality of life of people and the economic growth of the country. So, but for those of us who have had the privilege of working with you over so many years, it is fascinating to see how your professional journey has influenced your leadership style and your deep appreciation of data-driven decision-making. Your ability to connect real-world issues with strategic insights continues to inspire us. We look forward to seeing how your vision will continue to shape the future of IBIT that we all love and the University of Pretoria. So with that, thank you very much, and I wish you all the good things that are still ahead of you. You're still too young, so you've got many, many more years ahead of you. And to the family, continue supporting him. He is a treasure to the road industry. He covered a very small percent of his contribution to the road industry. Internationally, he's well recognized and respected for the contributions he's made. If you go to California, some of us have had the opportunity to travel with him. You go to California, the California Transport Department knows that they are where they are. The quality of their roads is where it is because of people like Prof Steyn. I don't want to take over. So, ladies and gentlemen, I'd like to extend my heartfelt thanks to everyone for joining us this evening. Your presence here, despite your other commitments and obligations, is truly appreciated. Special thanks also goes to the IBIT team, led by our faculty manager, Mrs. Managa Dever, for their tireless efforts behind the scenes in preparing for this event. Please be on the lookout for other lecture series forthcoming by our esteemed professors at the University of Pretoria and in our Faculty of Engineering, Built Environment and Information Technology. With that, please join us also for refreshments in the foyer and to continue chatting with each other, because I know some of us who have not seen each other for quite some time, and it is through this occasion that we are meeting. So please use this opportunity to talk to each other. there is also thunderstorm that is coming, so there's no need to rush and go home. So with that, please stand and remain standing while the procession leaves the hall. I hope you all have a good evening, Father, and good night.
Stone.